The date was November 24, 1944. Nearly 5.5 miles above Tokyo, Japanese fighter pilots pushed their aircraft higher through brutally cold air, engines straining at full throttle, desperately trying to intercept the American bombers whose white contrails streaked across the sky like chalky brushstrokes. The Nakajima Ki-84 Hayate, Japan's finest interceptor, struggled to reach 30,000 feet. When pilots managed to climb that high, they arrived exhausted, depleted of energy, with barely enough fuel and power left to observe the enemy from a distance. Inside those American bombers, the crew worked in relative comfort, wearing nothing but shirt sleeves, no oxygen masks, no heated suits. Their fingers stayed warm. Their minds stayed sharp. Below them, Japanese fighter pilots fought an impossible battle, struggling to maneuver in air too thin to sustain a real fight. Every other nation on Earth built bombers the same conventional way: more guns, heavier bombs, faster engines. But one Boeing engineer had looked at a luxury commercial airliner and asked a question that nobody else had thought to ask. The technology existed. The mathematics supported it. Yet the Army brass called it impossible. His own colleagues dismissed it as a 3,000-pound gamble that would get everyone killed. He built it anyway. When Japanese military commanders finally realized what they were facing, they grasped a bitter truth. America had created a bomber they could see in the sky, but could never reach. February 1940, Boeing's headquarters in Seattle. Wellwood Beale walked into a conference room filled with Army Air Corps procurement officers. They expected to see proposals that looked like every bomber design before it. More horsepower, heavier armament, bigger bomb payloads. The Vice President of Engineering carried something different, blueprints asking for something nobody had requested, and most would call insane. Heavy bombers in 1940 operated at ceilings between 20,000 and 25,000 feet. Crews wore oxygen masks connected to heavy bottles. The regulators froze solid in the thin, frigid air. Electrically heated suits kept men from freezing when the wiring didn't short out and fail. Men still suffered frostbite. Men still passed out from oxygen deprivation during missions stretching 12 hours or longer. The conventional wisdom was simple. Speed and firepower were your only real defenses. You couldn't outrun fighters, so you outgunned them. You couldn't dodge flak, so you armored yourself against it. Altitude was limited by how long human bodies could function in thin air. Beale remembered watching Boeing's 307 Stratoliner crews operating at 20,000 feet in 1939. Meanwhile, passengers in the pressurized cabin sipped coffee without oxygen masks, breathing comfortably. The technology worked. It added weight, roughly 3,000 pounds, for the reinforced fuselage and pressurization equipment. Beale had posed a question to his chief engineer that would transform everything. What if we brought that technology into combat? Ed Wells performed the calculations with the meticulous rigor that had established him as one of America's most accomplished aircraft designers. A pressurized cabin would add 3,000 pounds, yes, but operating at 30,000 feet or higher would place bombers beyond the reach of most enemy interceptors and anti-aircraft guns. The thin upper atmosphere created dramatically less drag. A bomber could fly faster burning the same fuel, and crews working in shirt sleeves at comfortable cabin pressures equivalent to 8,000 feet would remain mentally sharp, make superior decisions, and fly longer missions than frozen men sucking oxygen through masks that fogged and froze. The Army officers listened. Several looked doubtful. Pressurization belonged on airliners carrying executives, not combat aircraft that would get shot at over enemy territory. One small puncture in that pressurized fuselage, and the whole system would fail catastrophically. The weight penalty meant carrying fewer bombs or less fuel. The added complexity meant more maintenance headaches, more systems that could malfunction, more potential ways for the technology to kill the very crews it was meant to protect. Beale and Wells explained the mathematics carefully. At 31,150 feet traveling at 350 miles per hour, a bomber would operate in an airspace where current Japanese fighters simply could not follow. Japan's best interceptors maxed out around 25,000 feet under actual combat conditions. Even if they could somehow reach 30,000 feet, they would arrive completely spent, with no energy left for combat maneuvers, no speed remaining for pursuit. The bomber wouldn't need to fight enemy interceptors. It would fly in an arena they couldn't reach. The enemy could see the contrails. They could watch the bombers pass overhead, but they couldn't do anything about it. The brutal mathematics of aerial warfare inverted suddenly. Instead of building a flying fortress that survived through absorbing punishment, Boeing was proposing a bomber that won by simply never getting hit. Altitude itself became armor. The thin air became a weapon. That pressurized cabin wasn't a luxury amenity. It was the gateway to an entirely new altitude domain where American bombers would operate without opposition. The Army issued an order. Development commenced. By September 21, 1942, Eddie Allen, the test pilot whose judgment insurance companies trusted so much they offered lower premiums if he flew first flights, lifted the gleaming B-29 off Boeing Field's runway. The wing measured 141 feet across. 4 massive Wright R-3350 duplex Cyclone engines, each producing 2,200 horsepower. Revolutionary remote-controlled gun turrets allowing a single gunner to command multiple positions. And Beale's pressurized fuselage. The gamble Boeing's future rested upon. That initial flight demonstrated the bomber's extraordinary potential. It also revealed a fatal flaw that would claim 32 lives within 5 months. The Wright R-3350 duplex Cyclone engines contained high magnesium content in the crankcase. When these engines caught fire, and they caught fire frequently, the magnesium burned at 5,600 degrees Fahrenheit. Hot enough to melt through aluminum wing spars in seconds. Hot enough that fire suppression systems couldn't control it. Rear cylinders overheated because the cowling had inadequate clearances. Valves failed because fuel distribution was uneven. Oil leaked. Fuel leaked. When ignition occurred, those magnesium components became incendiary bombs, consuming the aircraft from within. December 30, 1942. Eddie Allen brought the second B-29 down from a test flight with No. 4 engine streaming ribbons of fire at 5,000 feet. He landed while the cockpit filled with smoke. The wing spar had already suffered damage. Structural failure was minutes away. Fire crews extinguished the blaze. Allen climbed out. The Army awarded him the Air Medal for saving the aircraft. 3 weeks later, he would climb back into that same bomber for another test flight. By then, President Roosevelt had made his commitment to Chinese leader Chiang Kai-shek at the Cairo conference. B-29s would be bombing Japan from Chinese bases by April 1944. When Roosevelt made that promise, fewer than 100 B-29s existed, and only 15% of them were actually flight-worthy. The Army had ordered hundreds more. Factory workers in Wichita were assembling bombers outdoors in temperatures dropping to 20 degrees below zero, working in rotating shifts of just 20 minutes to prevent frostbite. $3 billion invested, more than the $1.9 billion spent on the Manhattan Project. The most expensive weapons program in American history now depended upon engines that were destroying the very aircraft they powered. Wellwood Beale's revolutionary concept had produced a bomber capable of flying higher than any enemy fighter could pursue. But first, it had to survive its own engines long enough to prove the idea worked. February 18, 1943, 12:17 p.m. Boeing Field, B-29 serial number 1003, climbed through 5,000 feet with Eddie Allen commanding. The test flight was routine, checking repairs made after the December fire. Allen had flown burning aircraft before. He had landed bombers that should have killed everyone. His composure under pressure was legendary. Insurance actuaries trusted his judgment more than their own tables. No. 1 engine caught fire at 5,200 feet. Allen shut it down immediately, activated the carbon dioxide suppression system, turned the bomber toward Boeing Field, standard emergency procedure. He had done this before. The fire should have extinguished. It didn't. A second fire erupted. Radio operator Harry Ralston's voice suddenly cut through the intercom, stripped of the professional calm aircrew maintained even during crisis. Allen needed to get the thing down fast. The wing spar was burning badly. The B-29 was no longer an airplane experiencing engine trouble. It had become a structure being consumed from the inside by magnesium burning hotter than steel could withstand. The fire ate through hose clamps, valve housings, mounting brackets, every component connecting the engine to the wing. Parts began falling away. The bomber shed debris across Seattle neighborhoods as Allen fought to keep it in the air long enough to reach the runway. 3 crewmen jumped at 250 feet, dangerously low. Parachutes required at least 500 feet to deploy correctly. The silk canopies were still opening when the men struck ground. None survived. Allen kept flying. The runway was visible. Boeing Field was right there. The B-29 clawed through heavy air. The magnesium fire burned deeper into the main wing spar, the single structural beam keeping the wing connected to the fuselage. There was no saving the aircraft now, only determining where it would fall. It came down short of the runway. A meatpacking plant sat directly below. The bomber crashed through the roof at 12:28 p.m. Eddie Allen died instantly. 8 other crewmen perished in the impact. 19 workers inside processing meat for wartime rations were killed when 5,600-degree fire swept through the building. 1 firefighter died battling the magnesium blaze. The death toll reached 32. $3 billion evaporated. 32 aircraft destroyed. The most expensive weapons program America had ever attempted had just exploded across the skies above Seattle. Legislators in Congress demanded the whole thing be scrapped. Officers within the Army Air Force started wondering if the basic design was fundamentally broken. The engines were the obvious culprit, or so everyone assumed. It seemed crystal clear. Wright Aeronautical's R-3350 was tearing the bombers apart under power, yet no other engine could deliver the 2,200 horsepower needed at 30,000 feet. Time didn't exist to build a replacement from scratch. Roosevelt's deadline left no room for a complete redesign. Army brass handed Boeing a choice that seemed nearly impossible to accomplish. Sort out the engine problems, they said. Keep that pressurized cabin anyway, the one that added 3,000 extra pounds and shaped the entire design approach. Still hit the April 1944 deadline so these things can see combat. Otherwise, the whole program goes to consolidated instead, and you get the conventional B-32, an unpressurized bomber that throws away the altitude advantage that Beale had staked everything on. Spring and summer of 1943 turned into an intense struggle between clever engineering and political pressure. Boeing technicians, Wright specialists, and Army Air Force personnel descended on the R-3350 crisis with the kind of urgency that made normal development timelines seem laughable. The engine underwent tens of thousands of separate design changes, not just hundreds, tens of thousands. Everything that broke got rebuilt from the ground up. Every system that caused overheating got reworked. The cowling, that metal housing surrounding the engine, received a complete overhaul to push air harder over the rear cylinder banks. The original setup starved cooling air at low speeds, precisely when fully loaded bombers needed maximum cooling during the initial climb. The new design opened up pathways that almost doubled the airflow when the plane was ascending at full throttle. The carburetor setup was abandoned entirely. The early R-3350 had carburetors that blended fuel and air, then forced everything through a sharply angled passage into the supercharger. That tight bend caused turbulence that scattered fuel unevenly among 18 cylinders. Some ran too lean and overheated immediately. Others ran too rich and gunked up their spark plugs. Direct fuel injection changed the equation completely. Fuel sprayed straight into each cylinder in precise amounts, eliminating both the carburetor and that troublesome elbow. Hotspots vanished. Power output became steady and reliable. Metal shrouds called propeller cuffs were fitted around each propeller blade base to funnel cooling air directly toward the exhaust valves. These valves kept failing because temperatures pushed beyond what the metal could handle. Better cooling meant lower temperatures. Lower temperatures stretched valve life from barely 50 hours of operation to something approaching acceptable. Later production versions would replace the magnesium crankcases with steel. Steel was heavier, sure, but steel wouldn't ignite at 5,600 degrees like magnesium would. The first B-29s rolling off the line kept those magnesium hearts inside them. Those crews would fly into battle, understanding that an engine fire could become fatal in heartbeats. Even after all these fixes, the R-3350 stayed cantankerous. Engineers managed to stretch the maintenance interval from 100 hours to 400 hours by war's end, barely sufficient for engines that had to sustain 15-hour bombing runs. The R-3350 would claim B-29 crews throughout the war, but fewer than before, and enough aircraft would survive long enough to reveal whether Beale's pressurized cabin concept actually delivered. By May 1944, 130 B-29s had completed the grueling 11,500-mile crossing to bases scattered across China and India. Factory output was outpacing the rate of engineering improvements. Some arrived with every single modification installed. Others carried engines that had only partial upgrades. Every single crew knew they were piloting untested bombers straight into combat before the development program was even finished. June 15, 1944. The first B-29 strikes hit Japan since Doolittle's 1942 raid. 68 bombers lifted off aimed at the Imperial Iron and Steelworks at Iwata. 47 actually reached the target zone. 6 never made it back. The Steelworks survived the attack. Accuracy from that height turned out much worse than the planners expected. The weather acted worse than forecasted. Everything proved tougher than what the plans showed on paper. Congress and the critics circled like hawks. $3 billion. I see. Results that fell short. Crews still dying in the air. Yet the missions kept happening. Because buried inside the mission reports was something crucial, a piece of information that would reshape everything. Through summer and fall of 1944, a troubling reality emerged. One that both supported Wellwood Beale's original vision and revealed the R-3350's dark side. B-29s were burning on the ground, packed heavy with fuel and bomb loads on those baking tropical runways where heat pushed above 100 degrees. Left engines would overheat within moments of going to full power. These aircraft needed almost the entire runway length to unstick from the ground at maximum takeoff weight, 140,000 pounds. When fire broke out during that frantic climb, pilots faced an agonizing split-second decision. Abort the run and probably lie dive but lose the mission, or push forward and risk everything, hoping to get airborne. Early B-29 operations stacked the odds against survival by combining maximum weights with scorching field temperatures, overwhelming even the upgraded cowlings and injection systems. Engines would ingest their own valves, those critical exhaust pieces that cracked from thermal stress, then shatter pistons on their way down. When magnesium parts caught fire during takeoff, the inferno hit white-hot intensity. 5,600 degrees, so ferocious that main wing beams burned completely through in mere seconds, giving crews no opportunity to escape before the structure collapsed. Ground crews carved out small rituals, some muttering quiet prayers over engine nacelles before sealing them. Others ran through inspection routines that made no engineering sense but somehow felt sacred. Everyone watched other planes turn into funeral pyres at the runway's end and understood they could be next. The engines killed unpredictably, with no way to forecast which bomber would clear the air and which would become ash. Some ground crew simply bolted when engines fired up, unable to bear witness to another crew's death. But any bomber that got safely airborne and climbed to operational altitude entered a realm the Japanese simply could not reach. At nearly 32,000 feet, churning along at 350 miles per hour, the B-29 occupied a domain that Japanese interceptors could barely touch and absolutely could not fight in effectively. The calculations that Beale and Wells had worked out back in 1940 were coming true in actual warfare. Japan possessed no fighter capable of meaningfully attacking B-29s above 30,000 feet. The rare interceptors that could climb that high arrived completely exhausted, unable to maneuver for combat. November 24, 1944. Over 100 B-29s pounded Tokyo in the largest assault on the Japanese capital since Doolittle hit in 1942. Flying between 27,000 and 31,000 feet, the formations endured 184 separate fighter intercepts. Japanese pilots threw every defensive option at them, Ki-84, Hayates, Ki-100 Raptors, Ki-44 Shokis even weathered Zero fighters driven past safe operating limits. A crippled fighter rammed a B-29 directly over the target, destroying one aircraft, the only combat loss that day. B-29 gunners shot down 5 Japanese fighters. The remaining 179 attacks produced 0 kills. Japanese flak proved useless as well. Anti-aircraft cannons, built for 20,000-foot engagement, couldn't effectively reach 30,000 feet. Shells that did make the altitude took so long getting there that bomber formations just shifted position and avoided the predicted burst points. Pressurized cabins let crews observe searchlight beams and flak explosions through transparent nose sections. Reading the threat environment while maintaining tight formation, something physically impossible in unpressurized aircraft where oxygen starvation clouded judgment. The defensive gun system functioned exactly as designed. Computer-assisted remote turrets meant one operator could control fire on multiple targets simultaneously. The central fire director could swing all weapons toward threats individual gunners never saw, but altitude was the real shield. Any Japanese fighter that managed to climb high enough discovered the air too thin for meaningful engine power. They couldn't speed up, couldn't gain height, couldn't bank hard without dropping out of the sky. Those rare pilots who got themselves positioned correctly ahead of formations, the sole viable attack angle, could make a single pass before energy bled away, and they fell behind. Few Japanese fighter types possessed the speed above 20,000 feet to chase down these bombers, making the challenge of positioning interceptors at proper altitude ahead of the formations the crucial tactical obstacle. But even perfect positioning offered no guarantee. The Ki-84 Hayate, Japan's most capable interceptor, could just barely reach 30,000 feet when loaded for combat. Pilots operating at those edges were managing aircraft with almost no performance cushion. One hard maneuver risked an uncontrollable spin, tumbling downward through 15,000 feet or more before recovery, if recovery even happened. Every mission reinforced the same lesson. B-29s flying at designed altitude absolutely controlled the sky. Over 32,000 sorties rained down across Japan, with crews recording 914 confirmed aerial victories over Japanese fighters. The defensive setup performed flawlessly. The tactical approach worked. The fundamental concept Beale had sketched back in 1940, build a bomber that operates where enemy fighters cannot, turned out correct in the harshest possible examination, actual combat against a desperate adversary. By late 1944, Japanese aviators understood their situation with painful clarity. American bombers locked in formation at altitudes their interceptors could not effectively operate within, shielded by defensive systems they could not safely approach, carrying ordnance they could not prevent. Pressurized cabins kept B-29 crews mentally sharp through those exhausting 12 to 15-hour missions. No frostbite turning hands black and useless. No hypoxia degrading cognition and killing whole crews through simple mistakes. No electrical heating garments failing and leaving men freezing. Simply alert crews in comfortable shirt sleeves, making accurate calculations and handling complicated procedures while Japanese fighters struggled 5,000 feet below, visible through the bombardier's clear bubble, yet unable to climb any higher. The R-3350 engines still took lives unpredictably. Bombers still exploded on takeoff. Ground crews still whispered prayers. But the concept had proven sound. Wellwood Beale's audacious vision, the pressurized cabin that skeptics called too massive, too complicated, too fragile for actual warfare, had created a bomber that controlled Japanese skies through altitude alone. Then Curtis LeMay arrived in January 1945 and overturned everything. General Curtis LeMay examined the combat data with an engineer's dispassionate eye and reached a conclusion that unsettled everyone who grasped the B-29's purpose. High-altitude precision bombing was failing, not because the aircraft couldn't reach altitude or fight there. B-29s dominated the sky above 30,000 feet, but targets weren't getting destroyed. Clouds blanketed Japan constantly. Industrial facilities disappeared underneath weather systems that persisted for weeks. Bombardiers launching ordnance from 6 miles up through thick clouds were essentially guessing at map coordinates, not actually seeing factories. The bombing accuracy was devastating in its failure. That Norden bomb site, the closely guarded technology that was supposed to deliver ordnance into a pickle barrel from 4 miles up, turned into dead weight when clouds rolled in and obscured targets mere seconds before bombs fell away. The jet stream added another layer of impossible conditions. Winds screaming across Japan at 30,000 feet pushed speeds beyond 300 miles per hour. Bomber formations fighting headwinds inched forward like foot soldiers crossing unfamiliar terrain. When pilots took advantage of that same jet stream and flew with it, they tore across targets so rapidly that their bombing runs became pure guesswork. Those winds pushed ordnance miles off its intended path. Missions meant to obliterate manufacturing complexes left them standing untouched, while bombs churned up empty rice fields. LeMay recognized the problem, demanded something radical. Tear out most of the defensive weaponry to reduce weight. Pack the fuselage with clusters of incendiary bombs rather than conventional explosives. Fly low, somewhere between 5,000 and 8,000 feet, under cover of darkness. Strike when Japanese defenders couldn't spot the formations until they were already overhead. The irony cut deep. This bomber, engineered specifically to operate higher than any enemy fighter could climb, would need to win through flying lower than even their aging interceptors. That pressurized cabin, the breakthrough technology enabling crews to operate at those extreme heights, would become surplus equipment. Airmen would fly unpressurized at altitudes where they didn't need it, breathing easily in denser air while the elaborate pressurization system that Boeing had staked everything on gathered dust. The night of March 9th into 10th, 1945, Operation Meeting House dispatched 334 B-29s against Tokyo at lower altitude. They carried incendiary clusters meant to ignite the massive firestorms that wooden and paper cities would feed. The bombers pushed through searchlight beams that turned blackness into artificial day, through anti-aircraft explosions that claimed 16 aircraft, through ramming attacks by pilots resolved to take bombers with them into death. Roughly 100,000 civilians perished in that single night, exceeding the death toll of either atomic weapon. The firestorm consumed 16 square miles of Tokyo. Japanese defenses built for high-altitude interception collapsed against this shift in tactics. Searchlight arrays designed to illuminate bombers at 25,000 feet couldn't track aircraft diving through neighborhoods at 5,000. Anti-aircraft shells set to explode at high altitude detonated thousands of feet above the attacking waves. Fighter pilots scrambling for advantage discovered themselves locked in dogfights with bombers that spotted them coming and maneuvered hard at low altitude, where the B-29 performance characteristics were surprisingly generous. The lower altitude raids exposed something nobody anticipated. Those R-3350 engines, the power plants that devoured crews during high-altitude ascents, finally received adequate cooling. At 5,000 feet, the atmosphere carried density. Wind across engine cowlings rushed with force. Rear cylinder banks that cooked at altitude stayed manageable. Valve assemblies that failed from thermal stress endured. Magnesium components that ignited in thin air environments remained safely below ignition temperatures. The engines transformed from adversaries at 30,000 feet into dependable machines at 5,000. Yet those missions simultaneously proved LeMay's tactical revolution couldn't erase what Beale's original vision had established. Whenever altitude became mission-critical, when success depended on reaching higher sky, Japanese fighters remained powerless to stop them. That pressurized cabin functioned precisely as intended. It created an aircraft operating in airspace the enemy couldn't challenge. LeMay simply elected not to exploit that advantage during most sorties because low-altitude firestorm attacks demolished cities more thoroughly than high-altitude precision bombing. The capability existed nonetheless. The engineering concept was sound. Final vindication arrived through two specific missions that validated everything Beale had envisioned. August 6th and 9th, 1945. Enola Gay and Boxcar carried atomic weapons to Hiroshima and Nagasaki at 30,000 feet. Not one Japanese fighter came within striking distance. Interceptors that launched couldn't achieve operational altitude before B-29s cleared the targets. Anti-aircraft guns firing couldn't touch aircraft at 31,000 feet. The bombers proceeded to their release points at altitudes where they remained visible but unreachable, released weapons that ended the conflict, and returned without serious threat. The final tally spoke in contradictions. Total B-29 production reached 3,970 aircraft. Total expenditure came to $3 billion, equivalent to $52 billion in modern currency. Combat attrition in the Pacific totaled 414 aircraft from all causes. B-29s burned on the ground and fell from the sky, consumed by engine fires. Hundreds perished that way. B-29s shot down by Japanese fighters while operating at assigned altitude, negligible numbers. The R-3350 time between overhauls climbed from 100 hours to 400 hours as the war concluded, barely adequate for engines required to sustain half-day missions. Post-war development transformed that engine. Civilian versions with enhanced turbo compound designs powered Lockheed Constellations and Douglas DC-7s reliably through decades of service. Eventually, the power plant became trustworthy. Engineers finally possessed time to address problems wartime pressure had created. But during combat operations, the R-3350 remained lethal even after tens of thousands of refinements. Yet the B-29 succeeded regardless. That pressurized cabin enabled operations Japanese fighters couldn't contest when American leadership chose to use it. The atomic bomb missions proved the concept beyond question, as did every high-altitude strike where B-29s cruised above Japanese interceptors as though they didn't exist. LeMay's Firestorm offensive won faster, but one fact endured: the aircraft itself possessed revolutionary design that offered commanders Japanese defenses couldn't counter. Beale had proven correct. Fashion a bomber that flies above enemy reach, and you don't need superior guns or speed. The engines remained wrong. They threatened crews from first test flight through final combat sortie. Yet America triumphed because one engineer gambled that altitude equaled protection, and rarefied air meant advantage, and 3,500 pounds of pressurization gear meant more than 3,500 pounds of ordnance. He constructed an airplane operating at warfare 7 miles above ground level, and when Japanese fighters climbed as far as their machines allowed, they gazed upward, watching silver bombers dominate sky they couldn't attain. The B-29 paradox existed in that space between design intent and actual combat application. LeMay's lower-altitude Firestorm campaign destroyed Japanese cities faster and completely than any high-altitude precision approach. That pressurized cabin, the technology anchoring the entire $3 billion program, stayed mostly idle during missions incinerating 67 Japanese cities and killing hundreds of thousands. Yet dismissing the pressurization concept as failure required overlooking what occurred when commanders deployed it. The strategic tension ran deeper than simple tactics. LeMay stripped guns to carry more incendiaries, yet kept that pressurized fuselage untouched. The weight penalty Beale had incorporated, 3,500 pounds of reinforced fuselage and pressurization apparatus, remained aboard every aircraft despite altitudes where crews didn't require it. That mass could have been additional ordnance or fuel. But removing the pressurization system meant completely redesigning the fuselage, and no time existed for that. So the capability traveled every mission, dormant yet present, standing ready for moments when altitude advantage surpassed payload importance. Those instances occurred more frequently than standard histories acknowledge. Mining operations in Japanese harbors and shipping lanes demanded precise weapon placement in particular waterways. Those operations climbed to medium altitude, where bombardiers could identify targets clearly, yet where Japanese fighters still struggled climbing to combat-loaded B-29s. Daylight strikes against particular industrial facilities, whenever weather cooperated, utilized altitude, reducing losses while maintaining bombing precision. The aircraft stretched across its complete performance envelope from 5,000 feet during Firestorm raids to 31,000 feet when operational needs required altitude advantage. The atomic missions brought everything into focus. Enola Gay and Boxcar required altitude for two distinct reasons having nothing to do with enemy opposition. First, atomic weapon blast radii meant delivery crews required substantial separation when detonation occurred. Releasing from 30,000 feet provided time to execute demanding escape maneuvers and reach protective distance. Second, the mission itself was too consequential to gamble. Operating at maximum altitude meant Japanese fighters achieving intercept would arrive too worn to engage effectively. The pressurized cabin made that feasible. Airmen reached targets in shirt-sleeve conditions, sustaining mental clarity for a mission where failure meant catastrophe. The human price for proving Beale's concept materialized in numbers showing both validation and loss. Eddie Allen and 8 crew members perished testing an aircraft not yet prepared. 32 dead in that Seattle disaster, hundreds more killed through engine fires during training and operational service. Each B-29 lost to mechanical failure represented airmen who died not fighting enemies, but fighting technologies promising safety at altitude, then delivering death on the runway. Yet those same crews, when they cleared takeoff and reached operational altitude, experienced combat unlike anything other bomber formations knew. B-17 and B-24 crews above Europe flew unpressurized through flak, taking random targets and fighter attacks, converting formations to wreckage. They endured oxygen masks freezing their faces, electrically heated suits failing, leaving men with frostbite demanding amputation. They decided matters while hypoxia dulled thinking, oxygen starvation they couldn't recognize until danger arrived. B-29 crews at designed altitude worked in pressurized conditions equivalent to 8,000 feet elevation. They consumed hot beverages. They traversed the fuselage without heavy oxygen apparatus. They stayed sharp through 15-hour journeys because altitude didn't assault their bodies. When Japanese fighters appeared below struggling upward, B-29 gunners engaged possessing absolute advantage. Relaxed, attentive, operating systems demanding mental precision to function properly. The ultimate B-29 accounting revealed success measured through contradictions. The costliest weapons effort during World War II, surpassing even the Manhattan Project, succeeded spectacularly while being applied differently than designers intended. The pressurized cabin driving development proved both vital and surplus, contingent on which sorties deserved consideration. The engines nearly destroying the program endured as hazardous throughout the conflict, yet matured sufficiently to permit operations. The aircraft engineered for high-altitude precision bombing won the war through lower-altitude area destruction, yet concluded that war with 2 high-altitude precision missions validating the original vision absolutely. Wellwood Beale's conviction that altitude advantage transcended firepower proved correct in ways exceeding individual raids. The B-29 compelled Japanese air defense to contemplate threats they couldn't adequately meet. Resources devoted to high-altitude fighters barely effective, anti-aircraft batteries cited for 30,000 feet engagement, defense schemes predicated on formations possibly appearing at design altitude. The mere fact of bombers capable of operating 7 miles overhead restructured Japanese defensive strategy, regardless of American commanders choosing lower altitude attacks. The engineering contribution was clearer. Every air force that could afford them adopted pressurized combat aircraft. Beale's 1940 conviction that crew efficiency and capability warranted matching guns and bombs reshaped every bomber and transport afterward. That pressurized B-29 fuselage wasn't luxury or failed experiment. It became aviation's template going forward. The R-3350 engines narrated another chapter. They remained lethal through war's conclusion. They consumed maintenance intervals faster than supply lines could support. They demanded maintenance personnel achieve the impossible, keeping aircraft operational. Yet they also delivered 2,200 horsepower per engine at altitudes where that output mattered, driving superchargers enabling 30,000-foot missions. These engines functioned as both the catastrophe nearly wrecking the program and the critical component making success possible, achievable. Post-war improvement work rendered them dependable power plants supporting civilian aviation decades hence. But bomber crews who flew them operationally never forgot the sound of cylinder failure beginning or magnesium fire consuming wing spar, or the certainty that each launch gambled existence against physics. 3,970 B-29s produced, $3 billion expended, 414 lost in combat, hundreds more lost to the engines propelling them, and zero, precisely zero, downed by Japanese fighters, while at the altitude Beale promised would render them invincible. The engineer proved right, the engines proved wrong. America prevailed because one man understood winning required not superior fighting capacity, but traveling where opponents couldn't follow.